Okay, so if you recall class, an AR1 process, autoregressive, will look like this. I provided the code actually to you. I provided you with the code. Okay, so this is the AR1 process class. By way of review, let's take a look at what the formula is. So the formula is x sub t is equal to a certain constant c, and then your phi, which is your coefficient, x sub t minus 1 is your log 1 times series of x. So I hope you're very clear about this. No? So this is just the time series, but log 1. Okay, so again, just to make sure that you understand it, suppose we have this series. Suppose we have, let's say 10, then 8, then 7, then 8, then 8, then 9. Okay, suppose this is this is a series. There are more numbers here. This is the latest. Okay, so let's 11, 9, etc. Okay, so this is your x sub t. Okay, this is the latest. Okay, so x sub t minus 1 is simply log 1. So we take the value before, okay, 1 day before, since it's x sub t minus 1. So this becomes your 8. This is 8. This is 7. 8, 8, 8, 7, 8. So same thing class. 8 and then 10, then 11, and then 9, etc. Okay? So your x sub t minus 1 will always have one data less. Okay? So let's suppose it's only up to this one. So now you're going to regress. We're going to model our time series using the data x sub t minus 1. Okay? So it's just like a regression model. But this time, what you're using are past values of your x sub t, of your time series. That's why it's called an AR process, auto-regressive. You're using past values of itself in order to model your time series. So if it was x sub t minus 2, okay, x sub t minus 2, which would be an AR2 process. So this time, we'll be getting 2 logs, okay? So from here up, or you can get the log of this, 8, okay, this one, up, 8, 7, 8, 10, 11, 9, etc. So this is your x sub t minus 2. Okay, so any model involving your time series, and let's say your log 1 plus your log 2, this now becomes your AR2 process. In our case, an AR1 process here, we said it's equivalent to a certain constant C, and then your coefficient phi, okay, times your series x sub t minus 1, which is this one class, this one, okay, and then plus a certain error term. This error term is, we know we have discussed this to be white noise, okay, white noise with mean 0 and constant standard deviation. Constant variance, sigma squared. Okay, and also last time we said that this can be expressed as a backshift operator. So another way to write this, because sometimes you might see this in textbooks or in literature, is to group your x sub t's together. So this will be x sub t, x sub t, and then I put this on the other side minus phi, x sub t minus 1, okay, and then it's equal to C plus epsilon sub t. Okay, then what we do, class, is we factor out x sub t. So this becomes, so we factor out our x sub t there, and then this becomes 1, okay, for this one, and then minus phi Okay. Now x sub t minus 1 class will now become b. Okay. B, actually b to the first power there. B 1 or just b. And what does this mean, class? If I distribute this, okay, this one, so that backshift operator b class, b x sub t is actually equal to x sub t minus 1. Okay. This backshift operator gets the lag of 1. If it's 2 class, then it should be x sub t minus 2. Okay, so again, class, the AR1 process can be expressed as x sub t is equal to c plus phi x sub t minus 1 plus epsilon sub t, or can be expressed as 1 minus phi b x sub t is equal to your c plus epsilon sub t. Okay, so don't be confused, class. You can sometimes you'll see this this expression 1 minus phi times b times x sub t, which is equal to c plus epsilon sub t. Okay, let me pause for a while and again ask class if you got this, class. Okay, thank you. Coverage yung data and data structures, yung video na pinapaano ko sa inyo up to dplyr, up to data wrangling. Okay. All right. So a few more things about your AR1. Okay, so we have already explained what x sub t is. That's your time series, original time series. C is your constant term. Phi is your autoregressive parameter. And epsilon sub t is your white noise, okay, with mean 0 and constant variance. Now, we want to know what's the theoretical mean. The theoretical mean, class, is different from your empirical or average, class. Okay, because you can get the average of x sub t, right? Just get the mean of this. Okay. The average of x sub t, class, or that's called your empirical mean or mean itself, is not the same as your theoretical mean. Okay. So what is your theoretical mean? Your theoretical mean, as discussed last time, is your long run average. Okay. Long run average. So on a long-term basis, the average of your time series will fluctuate around that value, theoretical mean. And how do you compute for the theoretical mean? If you know C, class, if you know the constant, and if you know phi, then your theoretical mean is simply theoretical mean, or epsilon, expected value of x sub t is equal to your constant divided by 1 minus your phi. Okay, so that's very easy to compute. If you know the model, if you know C, and if you know phi, you can compute for the theoretical mean, which I said a while ago is the average, a long run average. Okay, and take note, it's always when the assumption here is that absolute value of phi is less than 1. Okay, so remember, class, the model, your x sub t, it's difficult for me to go up. X sub t, class, no? X sub t is equal to, what was I about to say? Okay, this phi here, class, this phi. In order for this to be an AR process, class, AR1 process, your phi sub 1, this phi, should be less than 1. Okay, positive or negative can be negative 0.9, can be negative 0.3, can be negative 0.2. Okay, it can be negative 0.8, or positive 0.8, positive or negative, for as long as it's less than 1. Of course, it cannot be 0 class. Because if this is 0, then it ceases to be an AR process because you're not anymore able to regress your time series on its past value. If this is 0 class, then that means walang effect, no effect. X sub t minus 1, the log 1, cannot explain your X sub t. Remember, this is similar to a linear regression, where this is your regressor, this is your independent variable, quote unquote, and it's used to explain your dependent variable X sub t. So please take note that in an AR1 process, your phi should be negative, less than 1. So if this is 0 class, then it ceases to be an AR1 process kasi wala na to, di ba? If this is 1 class, it cannot be also class. If phi is 1, then this becomes class, this becomes a white noise na to. Parang residual na yan, class. White noise na to. If phi is 1, then this series becomes a white noise. Okay? Becomes a white noise. It's now dependent on just the previous past value. Okay? And if phi is greater than 1, okay, whether positive or negative, then that becomes a random walk. Random walk can be two types of random walk. Random walk with drift. With drift means that C is existing. This is not equal to 0. So that's with drift. So what will happen to your time series now is that it will meander. It will go anywhere. Okay, random walk na yung class. No? Or this can be 0 and it becomes a random walk without drift. Okay. Drift class, drift. Drift means to move, parang wander aimlessly. Drift. Random walk with drift if this is non-zero. Random walk without drift if this is equal to 0. Okay, so please understand that an AR process has this structure and that your phi, very important characteristic of your phi, it should be less than 1. Okay, it should be less than 1. The absolute value is less than 1, which means it can be positive, less than 1, or negative. As I said, can be 0.99 or negative 0.99, can be 0.2 or negative 0.2. Okay, so you can also compute for your theoretical variance, okay, but we'll not discuss that much. Okay, so this is your theoretical variance, and it's equal to, this is the variance of your time series, sigma squared, divided by 1 minus phi squared. Okay, so the variance can also be computed. This is also your long run variance, long-term variance. Okay, this is your empirical variance. You get the variance of your time series, and then if you divide it by 1 minus phi squared, you get your long run variance. Okay, and then you have your auto covariance and autocorrelation. So we'll not discuss that anymore. But what's important here is the stationary condition, this one. Your phi, absolute value of phi, should be less than 1. Okay? Okay, is that clear, class? Clear ba? Clear? Okay. Thank you. Thank you. Okay, so I think I didn't give, I'm not sure if I gave this note last time. I'll just share this with you. Control C. Just a few notes about the theoretical mean. Okay. And here I'm saying that the theoretical mean is not the same as your empirical mean. Okay. They may approach each other. They may become almost equal if you have a very, very long time series. Okay, but if your time series is quite short, then definitely they will never be really equivalent or exactly equal. When you say here approach the theoretical mean, quite close, no? That's what we mean by it becomes quite close to the theoretical mean. But it does not mean that they're equal. They will never be equal, class. And they will become quite close if the time series is very long. If the time series is very short, then they will be quite different. Okay, because the empirical mean, okay, the empirical mean, class, is affected by short-term fluctuations. Okay, but the theoretical mean, class, we're taking a look at it from a long-term perspective. So it's not affected so much by short-term fluctuations because you're taking a look at this on the long term. Okay, long-run behavior. Okay, so how about AR2, class? Very quickly, AR2. It is just the same as your AR1. Okay, may ano lang, class. The difference is that si AR2, class, we already discussed this. Kasi AR2, class, ang formula natin is, you know the formula already, di ba? The formula is you have a constant C plus phi1 x sub t minus 1 plus phi2 x sub t minus 2. So you have two lags here. Okay, that's AR2 process. Okay, so the order is 2. That's why you have two regressors, x sub t minus 1 and x sub t minus 2. I hope it's clear, class, what this x sub t minus 2, how you get x sub t minus 2. Okay, you just, for x sub t minus 2, you just get the lag 1, LAG, lag 1, which I illustrated a while ago. And same thing with x sub t minus 2, you use the lag 2. So yeah, if you have your original series, you remove the latest value. That will be your x sub t minus 1. Okay, or you remove the first the two latest value. That will be your x sub t minus 2. Okay, and also, class, just to quickly illustrate this, how do we write this in terms of a backshift operator? Again, put your x sub t all in one place, x sub t minus phi1 x sub t minus 1 minus phi2 x sub t minus 2, right? So that will be on your left-hand side, and this will be equal to C plus epsilon sub t. Okay, this is your constant, this is your white noise. Okay, so quickly, class, we can factor out x sub t. Okay, sorry, let me write that here. We can factor out x sub t here and then express this as a backshift operator. So this is 1, right? If we distribute this, x sub t times 1, that's x sub t. This one, class, is minus phi. Okay, x sub t minus 1, class, okay, can be written as b times x sub t. Okay, b times x sub t is x sub t minus 1. And then this one minus, this is minus phi1, and then this is phi2. So phi1 and then minus phi2. Okay, and then x sub t minus 2, class, can be written as b squared, b to the second, class. B to the second times x sub t means second lag. That's x sub t minus 2. So this is equal to C plus epsilon sub t. Okay, so again, class, just for exposure, because you might be reading some text or you might be reading some journals and you see, what's this B? That's called your backshift operator. Okay, and it's also a good way to express your model. Okay, as compared to writing it this way, you can write it this way. Okay, and then, class, you can also compute for the theoretical mean. The theoretical mean is, since it's an AR2 process, take a look at this. It's also C over 1 minus phi1 minus phi2. Okay, if you're analyzing, for example, a time series and then it's an AR2 process, you can mention that the long run average of this time series is your constant C divided by 1 minus P1 minus P2. So that's your theoretical mean mu. Okay, and then you also have the formula for variance, theoretical variance, your long run variance. And what's important here, class, is this one, the stationary conditions. Okay, if for the AR2 process to for this to be an AR process, dapat, class, yung sum ng Phi1 at saka Phi2 dapat less than 1. Okay, hindi pa pwedeng more than 1 yung pag inad mo sila. And then also, Phi2 minus Phi sub 1 should be less than 1. And also, Phi2 should be between -1 and +1. So these are your stationary conditions. Okay, so in general, class, in general, your ARP model would look like this, di ba? Ito yung ARP model natin. Yan. T minus 1, T minus 2, up to T minus P. P lags. Sa AR, di ba? P lags sa kanya, no? Okay. And you can easily write this as, di ba? Okay, just quick exercise, class. So this can be written as, 1 minus Phi1, Phi1B minus Phi2, B squared minus dot minus Phi sub P B to the P. Okay, B to the P, and then you have here your X sub T. Okay. And it's equal to C plus your error term. Okay, so it's basic algebra, class. And you can see here that this is really now, it's like an equation, class. It's like a factor. Okay, so that's for your ARP. And again, class, by definition, your epsilon sub T here should be white noise. Okay, white noise with mean 0 and constant variance. Theoretical mean is, okay, 1 minus Phi1, etc., up to minus Phi sub P. Also, your theoretical variance, okay, this is quite complicated, so I didn't show it anymore here. So it makes use of Yule-Walker equations. Yule-Walker equations, class, are very important for computing the partial autocorrelation function, which I'm going to discuss in a while. Okay, so just remember this Yule-Walker equation used for partial autocorrelation. Okay, so quite a complicated formula for autocovariance and autocorrelation. And then, class, here, the roots. Okay. So if we solve for 1 minus Phi1 Z minus Phi2 times Z minus Phi sub P times ZP. Okay, so you're replacing the B, class, with the variable Z. Okay, and if you compute for this, okay, whatever solution you get here, the answer should be, it should lie, okay. So you have your unit circle here. The solution should be all outside the unit circle. I'll explain this more, class, later on, but that's what that means. So hindi pa pwede yung Z equal to 1. Hindi pa pwede yun inside the unit circle. Okay, so I'll just discuss the MA, class, the MA, and then we will go now to the main topic today. I just wanted to make sure that this is very clear to you, class. An AR process is a process where we use the past values of your time series to model your time series itself. Okay, so how do you determine if it's an AR1, AR2, AR3? Well, I'll discuss that in a while. We actually have to look at some plots called autocorrelation plots and partial autocorrelation plots. Okay. However, ngayon class, it's a lot easier because we have R or Python as a software in order to determine the type of AR or MA process that we're modeling. Okay. So distinguished class from your AR process is your MA. So yung MA class, pare-pareho lang din naman yan, no? MA1, MA2. Okay, so let me just show the model for an MA1 process. So this one class, this is our model. And you take note class that in the MA model, the constant is your mean, mu. So sa MA process class, the constant is already your theoretical mean. Unlike in the AR process where you have to compute for your theoretical mean, you have to use C over 1 minus P, right? For an MA process, it's already the mean class, this one. So, and you notice class, what is modeled is your epsilon. Okay, remember class, your epsilon, this is your white noise. This is a white noise. Okay, this is individually and independently distributed, okay, IID with zero mean and constant variance. So this is the nature of your white noise. Okay, now let me just be clear. The white noise here, the epsilon sub t, is not the error that you generate from your AR process. Because you might be thinking, how is the error generated here? Okay, how is the error generated? It's not the error from your AR process, right? Because in your AR process, you have your actual value minus your model value. So you'll have a residual, the difference between your actual and your model value. The value there, class, it's not the same as the error here. Okay, so the error here, class, is computed by certain parameters, no? And let's say one of the methods used is maximum likelihood estimation. So the process is quite difficult. Okay, but good thing there's already a software, so we don't have to worry ourselves with the computation. But what's important here, class, is that here you're modeling the errors, class, and the errors are they're white noise with zero mean and constant variance. Okay, so going down here, okay, as I said here, class, epsilon sub t and epsilon sub t minus 1 are white noise terms with mean 0 and variance sigma squared, which means constant variance. Okay. Excuse me. And then your theoretical mean, class, is there already. It's in the equation. So you don't have to compute for the theoretical mean. So for an MA process, the value that you get there is already your theoretical mean. Okay, and then the theoretical variance can be computed using this formula, 1 plus your theta squared multiplied by your variance. Okay, and take a look at this, class. Okay, here you see invertibility condition. Okay, for AR process, it's what we call stationarity condition. For an MA process, it's called invertibility condition. So let me just share this with you, class. Okay, I'm not sure if I discussed this with you, but Control C, Control V. Okay, So let me just explain, class, the invertibility condition. Okay, assuming, class, that you have this model where your theta is less than 1, class, absolute value of less than 1, then, again, class, your theta for an MA1 process cannot be more than 1, cannot be equal to 1, class. Okay, neither can it be equal to 0, kasi pag 0, class, then walang MA process. Okay, now this means, class, that if the theta, the absolute value of theta is less than 1, okay, which means that it's indeed an MA process, then we can actually invert. Okay, we can convert or invert the MA process into an AR process. So the MA process and the AR process are related to each other. So take a look at this. The model x sub t will still be a function of your theta, theta. However, theta is, okay, multiplied with your AR process, yung past values of itself. So hindi siya yung class, hindi siya yung epsilon. And take note, the limits are from j is equal to 0 up to infinity. Okay, infinite AR process. Okay, so a finite MA process can be converted into an infinite AR process. Same thing, class. An AR process can be converted into an infinite MA process. So if you take a look at this, the one that I shared with you, class, here. So this can be written, class, as x sub t is equal to epsilon sub t phi theta times x sub t minus 1. So take note, class, it's theta times not epsilon sub t minus 1, but theta times epsilon, theta times x sub t minus 1, theta squared x sub t minus 2, theta cubed x sub t minus 3, infinite, okay, infinite series minus dot. Okay, and take note of the alternating, no? Minus, plus, minus, plus, minus theta to the 5th, plus theta to the 6th. Okay, notice lahat ng mga even numbers, naka-plus siya. Lahat ng mga odd numbers, naka-negative siya. So what does this tell us, class? An MA process and an AR process are actually equivalent. Okay? An MA process and an AR process are equivalent. Okay, so ito, naulit lang to kanina, no? Up to theta. All right, so let me stop there, class. Okay, same thing lang naman yung sa MA2 at saka yung ARMA PQ. Okay, so let's go now to, okay, so yung lesson natin ngayon, I'd like us now to start with starting with an ARIMA process, no? Okay, so I don't think, have I shared this with you, class? Okay, so let me just share with you. So you may just open a new RMD file, class. You may open a new RMD file, Control C. I hope Canvas or Zoom will allow me to share this. Okay, sometimes it doesn't. Okay, so I leave you, class, to, these are very good references, or you can use other references. So do read about ARIMA, class. Okay? Do read about the AR process, MA process, although we have discussed the qualities, the attributes. Okay, it pays to study them also. Okay, so these are the packages that we need. Okay, make sure, kindly check. Now, another package that we need is TSM. Okay, so I think I'll have to put here course is equal to 2. I'm having problems with my TSM, but we'll be needing this class, this package, TSM package. Ang problem ko, class, with my TSM is that it is naka-install na, no? Pero may mga ginagamit akong functions. I'm using certain functions that do not run with that do not run, even if I have loaded my TSM class here. So make sure, class, kindly check in your packages if forecast, okay, and this one again. Okay. Now this one, I have a problem with this one because okay, I want all, however, class, one, all, enter. Okay, sometimes it doesn't work. I hope it works this time. From my experience with another class yesterday, glue, okay, CLI successfully unpacked, color space, okay, in your case, class, kindly check in your packages window pane, TSM, and please kindly check if it's loaded already. If not, kindly check, class. So done, TSM. The same thing yesterday, class. Uh, I'm redoing this now because yesterday, even if this package was already loaded, there were some certain functions in TSM that was not working. So that was my problem yesterday. All right, kindly feedback, please, if you have the package loaded. Okay, good, good. Thank you. Okay, so again, let me. Okay, I hope this Control C. So here are a few notes, class, for your. So sometimes it's so exasperating that R will not allow Fox Jenkins, then maybe up to step, let's see, step 4. Control C. There we go. Okay, so step 4, and then let me share this step 5. Okay, I don't want to risk class. Up to overtime, Control C, Control V. So let me just first share the notes with you. Okay, let me check. Up to here, Control C, Control V. No. So up to where did I, overtime, changes overtime, where's that here? Okay, so 73 up to 84. 73. That's a short line, 74. So sometimes it's, I don't know what the parameter or what the requirement of 81 to 88 Control C. Okay, let me stop there, class. Okay. Right. So quickly, class, let's go to the process of doing an ARIMA class. Okay. So there are many ways to model your time series. One of the most popular way is the Box-Jenkins approach. I think I told you to do some reading about Box-Jenkins approach. Okay, so I'll not provide some details. So just do some research, some reading on what this method is. Well, it's actually the ARIMA process. And as we know already that the ARIMA process makes use of the past values of itself, that's AAR, MA, the past error terms, and I stands for integrating or differencing. Okay, so what does integrating or differencing mean? It means, class, that, so let me just briefly give an illustration. So let's suppose we have our time series data, let's say 10, then 9, this earliest, 9, 7, 8, 8, 7, 9, for example. So this is the latest value. Now, a difference time series, class, means an integrated time series means you're using a different time series. So this is your x sub t, a difference or an integrated one, ARIMA, no? Yung ID to class, integrated, means that what you did was to get the difference. So 9 minus 7, that's 2. 7 minus 8, that's negative 1. 8 minus 8, that's 0. 8 minus 7, that's 1. 7 minus 9, negative 2. 9 minus 9, that's 0. 9 minus 10, negative 1, etc. Okay? So take note of this, class. This series of integration 1, because we're subtracting it for ones, no? So I'm calling it D difference x sub t. Okay. So when we use ARIMA with an integration, we're actually using now a different time series. This is no longer the original time series. It's now a difference time series. Okay, so this is what we're going to model if it's an ARIMA where I is equal to 1, difference 1. It can also be I is equal to 2. So which means you go do another differencing. 2 minus negative 1, that's 3. Negative 1 minus 0, that's negative 1. 0 minus 1, that's negative 1. 1 minus, what's this? Whatever, no? So this is now it can now be your D2, second differencing of x sub t. You can name it D2 x sub t, second differencing. Okay, so you can have that one, class. And why do we difference, class? We difference because we need to transform our data into a certain type of data so that we can use the Box-Jenkins approach. Okay. So what is the quality, what is the characteristic of the data so that we can use the Box-Jenkins approach? Okay, so let me discuss that now. Okay. In order for us to be able to use the Box-Jenkins approach, we say that the data should be stationary time series. Okay, may I ask you, class, if I discussed with you last time what a stationary time series is? Oh, hindi ko pala, sorry, hindi ko na-send to, class. May I ask you, class, what is it? Did we discuss what a stationary time series is? Can I chat, please? Yes or no? Have I discussed that with you? What is a stationary time series? Very briefly, yes. Okay, so yeah, I think I discussed this with you, but just a quick review. So when you say stationary, class, your time series should have constant mean and constant variance. If you recall, class, I gave an example where we plotted your time series. And if your time series behaves this way, okay, so it moves within this band, class. So this is an example of a stationary time series. Why? Because the mean is constant, okay, across time. So you have constant mean And also the variance is constant variance. So these are two characteristics of a stationary time series: constant mean, constant variance. And what is a constant mean, class? Here, it means that it does not have a trend, because it's different, class, if your time series behaves this way. So this time series, class, if you take a look at this band, okay, at this point, the mean is around this one. However, at this period, if you're looking at it, if you're looking at it this time in this period, the average is now this one. Here, the average is around this one. Here, the average will now be around this amount. So you can see here that the trend results into a non-constant mean. Okay? Now, the variance may be constant, no? Kasi yung fluctuation niya, okay? Ito, class, constant variance nito. Kasi yung fluctuation ng data natin is just around this band. No? However, if your data now behaves this way, okay? All right, take a look at this, class. The mean is constant, okay? No trend. Okay, any point in time, class, even at this point, the mean is still this one. Okay, because you have high values here and low values, they'll just even out. Okay. However, class, the variance is different. Here, the variance is now, okay, it's not very high. Here, the variance is just here. The variance now is about this one. The variance here is now about this one. So now, the mean is constant, but the variance is not constant. So remember, for a stationary time series, it has to be both mean and variance should be constant. Sometimes both are not constant, like this one. So if you have a data like this, so it has a trend here, okay, and then the variance is also increasing. Sorry for the illustration. Okay, the mean is not constant. Okay, the mean here around this period is around this one, but when you go here, the mean is now higher. Here, it's much more, it's higher still. And then the variance, okay, the fluctuations is not constant. So in this case, you have non-constant mean, non-constant variance, and it's non-stationary, okay? Constant mean, variance not constant, not stationary. Constant variance, mean not constant, not stationary. Not constant mean, not constant variance, also not stationary. When will a time series be stationary? Constant mean, constant variance. Okay? So clear ba yung class, yung concept ng stationary time series? Kindly please chat. Kindly please confirm if it's clear to you. The concept of stationary time series. Okay, waiting for your response. Okay, good. All right. So how do we now do ARENA? So these are the steps, class. First step, plot muna natin. Let's plot the data and let's see if it's stationary. If it's not stationary, then you will have to transform the data. Okay? How do we transform the data? It depends, class, on how your data looks like. If there's trend, say there it behaves this way. There's a trend, but the variance is constant. The fluctuations is constant. So this is non-constant mean, but constant variance. In this case, you can do differencing. Right, class. Remember the differencing we did a while ago? So what will happen now is you're going to model a time series that's not the original. Okay? And you might be asking me, if we're modeling now a time series that's not the original, then how do I now forecast? Because now you're dealing with a different time series. That's a very good question. But what will happen is that, because remember, why are we modeling? Because we want to forecast. That's one of them. We want to understand our data, and we want to forecast it, let's say, in the next 2, 3, 4 steps. So if you're now going to use a different time series, then your data is now different class. But still, you model this. If the mean is not constant, which means there's a trend, you can differentiate. And when you differentiate, you're now using a different time series. Okay, so you model that, and then you predict. What will happen is that you will have to revert back. Okay, you will have to what we call integrate it back to the original data, so that you get the real forecasted values. Okay, I hope you get what I mean, class. Because when you differentiate your data, you now have a different data time series data. Okay, having a different time series data class, and then you forecast it. Of course, the values will be off because it's no longer the original time series. And for a company, for example, of course, they would want the forecast of the original data, not the difference time series. So there's a way to go back. Okay, so no problem with that. Okay, so if there's non-constant mean, then you can difference the data. Oftentimes, differentiating the data will treat that. Sometimes it does not. It does not. So maybe you need to take another differencing. Okay, so sometimes you might need 2 differencing, but oftentimes, class, 1 differencing might suffice. Okay, now what about if there's non-constant variance? So for example, your database this way, there's a fanning out class. Parang it's like a fan, no? There. It's like a fan class. It's like a funnel, or it can be the reverse this way. From here to here. So this is non-constant variance, non-constant variance. So what do you do with that class? What you do, class, one way to convert this into a stationary time series is you get the log transform. So whatever the value of your data is, you get the log of that, then it's possible that the non-constant variance will become constant. Okay, so what will happen now is you're going to use another data class. It's a log data. Okay, so you do transformation, because if you don't do transformation, then your data is not stationary, then you cannot use ARIMA. Okay, you just have to use another model. But if you're going to use ARIMA, which is a very powerful method, which is very robust and easy to implement actually, then you'll have to do some data transformation, because that's the first requirement. Dapat stationary yung data natin. Okay, now what if there's if it has a trend, and if the variance is not constant, so like this. So you might need 2 processes. You might need differencing and then taking the log. Okay, now how should you do that, class? Should you take the difference first and then get the log, or the log then take the difference? The answer is you have to first get the log, class. Get the log and then get the difference. And why is that so? If you get the difference first, then a great chance will be there will be negative values. And you cannot get the log of a negative value, class. Okay, so you don't do it this way. Don't difference and get the log. Otherwise, you'll have NANs, not a number, because the log of a negative number is undefined. Or, okay, the other option is get the log and then get the difference. So this is okay, class, because getting the log, class, and then getting the difference will not have any problem. All right, so as I said here, if both transformations are to be performed, then get the log first, log transform, and then get the differencing. Okay, so let's suppose we have done that. Okay, you have gotten the log and then gotten the differencing, and then it turns out, class, it looks like your data seems to be stationary just by visual inspection. You don't stop there, class, because you will have to check statistically. Okay, check statistically if our data is indeed stationary. So there are statistical ways to do that. So the two most popular ones are the ADF test. This is augmented Dickey-Fuller test. And this is Kwiatkowski, Phillips, Smith, and something. KPSS, these are the names of the persons. So this will statistical test if our time series is stationary or not. So it's not enough for us to do transformation and then do a visual inspection, plot the data. We have to do some statistical tests. Okay? So let's suppose that okay na yung statistical test natin. Then the next step is to plot the autocorrelation function and the partial autocorrelation function. Let me illustrate what the autocorrelation function is. So let's go back to our example. Okay. Once again, we have our data. For example, you have 10, 8, 8, 9, 7, 8, 6, 9, 10. For example, only class, etc. No? This is our x sub t. Okay. Then what we do, class, is get the autocorrelation. As the name suggests, class, autocorrelation. We're getting the correlation of the time series with itself. It's auto. So what do we do? What do we do, class? We get, for example, the autocorrelation function, autocorrelation of your time series with its log 1. So your log 1 will be 9, 6, 8, 7, 9, 8, 8, 10. Okay, I hope you're getting me, class. You just get this log 1, okay, and compare it with the original time series, and then you get, class, the correlation of this. Remember, class, you can easily get the correlation of two sets of quantitative variables. So you get the autocorrelation. So that will be your autocorrelation at log 1. Okay, then you also get the autocorrelation at log 2. So what happens? You get now log 2, 6, 8. So this is two days before, right? 7, 9, 8, 8, 10. And then once again, you get the autocorrelation between this original and your log 2. Okay, so that will now be your autocorrelation at log 2. Correlation between this one and this one. And then and so on and so forth. So you do that for log 3, log 4. Okay, you can do it for log 36. Okay, because sometimes if there's seasonality, you can see that there's correlation between log 1, 1 and 12, 1 and 24, 1 and 36, because let's say it's a monthly, you have monthly seasonality. Then there should be correlation among the, say, January and January of next year, February and February of next year. That could happen. There's correlation. There's autocorrelation. Okay, so, and then you plot, class, whatever correlation you get here. Okay, correlation at log 1, correlation at log 2, correlation at log 3. You have the values there, and then you plot it. The plot that you'll generate is called your ACF, autocorrelation function. Okay, so it's just the correlation of your original data and log 1, original data and log 2, original data and log 3, etc., etc., etc. Okay, nowadays, class, we can use R to easily show the autocorrelation function. All right. Then next is you also plot the partial autocorrelation function. Now, the partial autocorrelation function is quite tricky, no? Kasi ganito, no? So, okay, so we have now autocorrelation at log 1, autocorrelation at log 2, autocorrelation at log 3, diba, class? Autocorrelation at log 4. We compute for that. How do you compute for the partial autocorrelation? Okay, so the partial autocorrelation, let's say, partial autocorrelation for log 1 will just be the same as the autocorrelation for log 1. Pareho lang siya. Pero class, pagdating dito, partial autocorrelation at log 2. Your partial autocorrelation at log 2 will be your autocorrelation at log 2 minus the autocorrelation at log 1. So lahat ng intervening class, no? Ima-minus natin to get your partial autocorrelation. Okay, for example, you have your autocorrelation at log 12. Okay, so you're able to compute for this, right? Diba? What will now be your partial autocorrelation at log 12? Well, it will be your autocorrelation at log 12 minus the autocorrelation at log 1, log 2, log 3, log 4, log 5, hanggang log 11, class. So si partial autocorrelation at log 12 is your autocorrelation at log 12 minus lahat ng mga intervening or intermediate, which are your autocorrelation log 1, log 2, hanggang log 11. Okay? Okay, so most probably class, ang autocorrelation natin, usually class, but not autocorrelation will be lower than your partial autocorrelation will oftentimes be lower than your autocorrelation. Okay, let me pause for a while, class. Kindly please chat if clear yung concept ng autocorrelation at saka partial autocorrelation. Kindly chat please, class. Autocorrelation function, so makukuha natin mga values yan. And then the partial autocorrelation function, we get the values, partial autocorrelation 1, partial autocorrelation 2, hanggang whatever, hanggang 36 kunyari, o 48, depends on what you want. You get the values there, and then ipa-plot siya. Okay, good. Good, thank you. So, okay, which do you think is more difficult? The ACF or the PACF? Pakichat nga, please, class. Ano mas mahirap gawin? ACF or PACF? Isa lang sumagot, class. Waiting for the others to answer. ACF? Bakit ACF? Mas mahirap? Bakit? Bakit ACF, class? Bakit, Mark, bakit PACF, class? Mark, Sir Benaventura, bakit mas mahirap si PACF?
Sir, kasi di ba you have to
O kunyari, Mark,
have
kunyari, let's say, how do you compute for the ACF ng log 12? How do you get the autocorrelation? Diba, kunin mo yung original data, tapos kunin mo yung log 12, yung 12 data before, diba? Tapos i-partner mo with the original data, tapos kunin mo yung correlation nila. Class, clear yun, ha? Clear. Ang autocorrelation is just get the correlation between the original data and kung log 12, kunin mo yung 12, tanggalin mo yung first 12, okay? Tapos isama mo lang yung yung next hanggang dulong-dulo. And then pair it and then get the autocorrelation. So that's the autocorrelation for log 12, di ba? Si partial autocorrelation for log 12, iba, class. Okay? Iba siya, class, kasi si partial autocorrelation, it's equal to the autocorrelation at log 12. Okay, walang problema. Kasi actually, na-solve na natin to, di ba? And then you'll have to subtract the autocorrelation at log 1, autocorrelation at log 2, minus autocorrelation at log 3, minus autocorrelation at log 4, minus autocorrelation at log 5. Okay? O, ulitin ko, class. Ulitin ko yung question ko. Sino mas mahirap i-compute? Si ACF o si PACF? Okay. Pakichat nga, please, class. Para nagkakaintindihan tayo. Which is more difficult to compute? ACF or PACF, class? Ayun. Okay, good. Thank you. Klaro na, ha? Klaro na. ACF, kunin mo lang, class, yung log. Okay, kunyari, autocorrelation at log 36. Eh di ang gagawin ko, tatanggalin ko lang yung first 36 values ng original. So doon ako magsisimula doon sa 37th, no? Tapos ibababa ko na yun, ipaparis ko na yun doon sa original time series. Okay? Just make sure that pareho sila ng number of observations. And then I can easily get the correlation of that. So that will now be my autocorrelation for log 36. Eh ngayon, si partial autocorrelation naman. Okay, gagamitin mo yung autocorrelation at log 36. No? And then ima-minus mo. Lahat ng autocorrelation from log 1 hanggang log 35. Tanggalin mo yan. Lahat ng mga intermediate, all the intermediate effects. Minus, minus, minus. autocorrelation 1, autocorrelation 2, autocorrelation 3, etc. Therefore, class, obviously, the partial autocorrelation function is more difficult to compute and it's more difficult to set up. Okay? That's why you need, remember a while ago I said yung Yule Walker, okay? Kasi ang hirap gawin yan, class, lalo kung manual. Buti na lang, class, may mga functions sa R that can already compute for the partial autocorrelation function. And it makes use of that, what we call the Yule Walker equations. So pinapadali niya because of that. But we're not going to do that manually kasi it's really involved, class. But actually, class, kung nakuha mo na lahat isa-isa, no? Autocorrelation 1, log 1, log 2, log 3, log 4, okay? Pwede ka na mag-minus na lang. Kunyari, autocorrelation at log 12. So what's the partial autocorrelation at log 12? It's autocorrelation at log 12 minus log 1, log 2, log 3 hanggang log 11. Ganun lang, no? Okay, so ipa-plot natin, class, si ACF at saka si PACF. Okay, now why is this important, class? This is important, yung plotting, class, kasi we will now be able to see, class, kung anong time series yan. Kung anong model yan. Is it an AR model? Is it an MA model? Or is it an ARMA model? Yun ang gamit ng class, no? Yung ACF at saka PACF. So with that, class, once you have the ACF and the PACF, okay, you're able to identify. Kaso ano pa rin yan, class, iterative pa rin yan. Kasi sometimes just by looking at your ACF and the PACF, mahirap ma-determine, class, kung AR yan o MA. Okay? Ang class, ang okay, ACF, no? Let me just illustrate this very quickly. ACF, and then this one is your PACF. Okay. Ang AR process, class, ang PACF niya ganito. So you have these lines, you have these lines. Ang PACF niya parang ganito. Then, may line dito, tapos lahat yan, ano na, insignificant na. Tapos, ang ano niya, ang ACF niya, it looks this one. Parang decay, ganyan. Okay, so, of course, medyo mahirap nyo ma-visualize. Ano? Sinasabi ko lang. So, we'll have an example. Aabot tayo. I just want to get to this example para nakapagsimula tayo ng isang example ng AR process. Okay? Then we identify the best model, class. After we identify the best model, we can forecast. Okay? And then once we forecast, class, we have to check. Okay? Or in fact, step 9 dapat to. No? Kailangan i-check muna natin kung okay yung model natin. So you don't forecast first. You check if our model is okay. Okay, kasi pag nag-model na tayo ng AR o MA, magge-generate yan, di ba, ng residuals, yung epsilon sub t. Yung residuals, class, ng model, not the MA white noise, no? Yung residuals natin. Okay. All right. So let's have an example, class. Okay, dinescribe ko lang dito what a ito, class, no? So let's do this quickly. Okay. Control C. I think ginawa natin to kasi last time. Okay. Ginawa ba natin, class, air passengers, please? Did we do air passengers last time, class? Pakichat, please. Hello, class. Did we or did we not? Share the code chunk. Okay. Anyway, class, so itong data na to, yung air passengers, it comes preloaded with R. So it comes with the datasets package, so that it can be easily obtained. So kunin natin, class, yung data na air passengers, run natin to, and then you can see now under the environment that sa environment, class, makikita natin that it is nasa value siya, air passengers, no? So it's a vector. It's a time series vector, 144 observations. So let's create a shortcut, AP class. AP is, we're creating this object para maiksi lang yung pangalan kasi ang haba nito. Air passengers, let's run this. And then let's print yung AP natin. So ito class yung AP natin, double 144 times series. This is a vector, 112, etc. And we can plot this. So let's plot this para makita natin yung behavior niya. Understanding the AP object here. Okay. So let's see. Okay. If you run those class, una ipiprint. Pag AP, ipiprint yan, ano? It will be printed, yan, AP, and then structure, and then sum, may missing value ba, class? Is there a missing value? Walang missing value. Then, tingnan natin class yung frequency. Okay, 12, which means this is monthly. And then cycle class, tingnan yung cycle. Ayan. So, ang cycle niya, pag January 1 hanggang December 12. Pag 1951 ulit, 1 up to 12. Okay, so that's a cycle. This is a monthly class. Monthly data. Yun ang ibig sabihin ng cycle. Okay. And okay, I'm going quickly over this class kasi oh. Bilis. Wala. Okay, plot natin class. Is this stationary? Definitely not, class. Hindi ko pa yata na-share to. So, I'm sorry, I wanted you to write this, to write the code here. Pero class, medyo ano na tayo sa oras, no? I'll just share with you this. Two codes, pareho lang naman yung class. No? Okay, itong tatlo. Control C. Control V. So we're trying to understand itong ano natin, itong air passengers data natin. Okay, so let's plot. Right. So the first one makes use of the plot function. We're plotting the AP object. You have the label for the x-axis, the label for the y-axis, and the label for the main plot. Run natin to. And we can see here, class, that here. Oh, class, tingnan nyo. But definitely not stationary yan. Why? There's a trend. And also non-constant yung variance. No? You can see, class, that if I draw a line here, there, class, there. Mukhang nagfa-fan out siya, no? Nag-i-increase over time yung ano yung frequent yung ano niya yung ups and low and downs niya, no? Okay, so non-constant to, class. Non-constant variance. Okay, you can also plot the other one, class. Pareho lang naman yung class, no? Okay, so I leave you, class, to plot this using ayan, using GG45. And this one also, this is very important. You run that, class, and then ang sabi ko kasi dito, i-cycle niya, no? Cycle ng AP. Okay, and take note yung cycle, class, di ba? 1 up to 12 yung every year, so ibig sabihin monthly. So ipapakita niya dito ang plot nito ng box plot is monthly. No? So lahat ng January ito, lahat ng February, March, April, kita natin sa ang pinakamataas na variance is July, no? Pati August. Tapos pinakamataas sila na average. Yan, no? Pinakamataas. Okay, dun sa number of flights. Okay, so you can see here, class, that indeed, kita natin na hindi constant yung average nito, hindi constant yung mean. Okay, among the months, nagpa-fluctuate siya. Okay, so, okay, anyway, I'll just give you this side notes. Okay, so it's already time, class. You may leave now. Tapusin ko lang tong konti, no? Control C. Control V. Okay. All right, so just this one, class. decompose natin. Okay. If you run this code class, makikita nyo na dine-decompose niya yung data natin na AP. It decomposes it into yung original data niya, ito. Tapos yung seasonality, pinapakita. Tapos yung trend din. So indeed, we can see here that this data has a trend and it has a seasonality. Okay, last class, last. Ito na lang. Control C. Control V. There. Okay, last class, this one. And if I run this class, so this is now class, the statistical test na sinasabi ko sa inyo, no? Okay, ang null hypothesis nito, the time series is non-stationary. So if we run this class, it will tell us that, okay, the p-value is 0.78. Ano yung null hypothesis? Time series is not stationary. What's our conclusion? Since the p-value is 0.78, we fail to reject the null hypothesis that the time series is non-stationary. Talagang hindi siya stationary based on statistical test. Okay, so na-confirm class yung visual natin, ang visualization natin, hindi stationary yan. Statistical test, hindi stationary yan. Okay, so let's end there class. We will continue with this next meeting, okay, and how to address this, and then we proceed now to the AR ARIMA process. Okay, so let me stop recording.